Ya. Hola, buenos días. Hoy tenemos al invitado al profesor Philippe Lours. Él viene de la Universidad IMT Minas Alpi y nos viene a presentar una charla sobre análisis de falla en componentes industriales. La charla será en inglés. Y Philippe, thank you very much for being here at the university. Yeah.
Thank you very much for inviting me, Jonathan. It's a real pleasure to be here with you today for doing this seminar. I will be spending the whole week at EIA upon the invitation of Jonathan and his colleagues. And it's an honor and a real pleasure to be here. I will do some lecture for students, some talk about our research activities as well tomorrow. And today is general speak about the general talk, sorry, about the failure analysis. So this is a talk we prepared together with my colleague from the University of Tulsa in the USA, Professor John Henshaw. That I would like to thank you today as well for giving some materials for doing this talk. So, as an introduction, I would say that the failure analysis of industrial components is a way to improve performance of parts in the industry, of course. We do failure analysis because we have to do, because some parts breaks or fail during service, but also the idea behind this is to improve the parts that we manufacture by proposing and recommending corrective actions. So we will go through this agenda. After a general introduction, we will talk about the reason why we do failure analysis, talking about statistics, which is very important in failure analysis. Some words about the failure reporting, because when we do failure analysis, we have to report what we find, and we have to report simply but factually what we do, what we did, and what we found, of course, and again here the corrective action we recommend. Then I will give you some example of case studies, starting with a very important thing, which is a failure chain. And I will give this example of the Lake Megalithic railway train, the catastrophe occurring in 2013 in Canada. So, as an introduction, I would say that the failure is a conjunction of two things. A defect in the material or in the design or in the manufacturing of the part, and a loading mode. So this defect can be either in the material selection, or also the process selection for making the material. Design defect, problem with the design of the part, and then machining defect or metallurgical defect due to the manufacturing shaping, the thermal treatment, or the welding as well of materials. And this can be also an inappropriate use of the part, an overload, a non-adapted temperature, and a non-adapted medium. And then you have the loading mode, which can be purely mechanical, static loading, dynamic loading, when the part is loaded in fatigue, for example. This can be environmental due to corrosion, due to dry or high temperature corrosion, stress corrosion, hydrogen embrittlement, and then friction with wear for surface damage of materials and bond. And then the failure coming from the conjunction of these two things, defect and loading mode, can appear through fractures that can be either ductile or brittle, that can be semi-brittle as well, that can be progressive or instantaneous. This can be only deformation without any fracture, and this can be usually coming from friction in weld, some superficial degradation or damage of the material or part. For understanding the reason of a failure in a part of natural, it's interesting to have a look on the life cycle of industrial product. First, the functional definition of the part is performed before manufacturing the product. Then you have to design and select materials and process to do and to manufacture the part. Then you do the manufacturing, you do the control and test, and you use the part that you have manufactured. Either the use is satisfactory and no failure occur in service, good behavior, or you have a failure. In this case, you have to analyze the failure and to recommend corrective action. And this analysis of the failure and the corrective action can take place in any of these parts of the cycle, life cycle of the part. Not maybe in the functional definition of the part, which is what it is, but on the design and selection of material, it can be on manufacturing, it can be on the control and test, and in the use it can be.
Can we do a little break because we have some problems with the.
We have to stop.
Yeah,
Okay.
just a little bit, just
Yes.
the,
Okay.
can
So
we?
I make a break.
Yeah, can we take the presentation and put it there?
Okay.
Here.
So what about the audience? Still
Yeah, they're
connected?
Yeah, yeah, they wait a little bit.
So I put on the.
Yeah, put it in the.
Sí, es por el vídeo del video.
I have just.
Pues ya la vamos a poner aparte.
Vamos a poner la presentación abajo porque.
Sí, porque se ve formal.
Ajá.
Where is.
El audio está relativamente bien.
El audio, ¿qué
El
tal?
audio está bien. Se siente un poquito apagado pues, porque es una acústica cerrada. Pero es que es demasiado bien. Pues, no sé.
Demasiado brillo. Vamos a colocar la presentación abajo, la presentación para que la vean.
Pues, puede ser mejor.
Analysis.
Creo que yo sí lo mismo. No traigo el micrófono.
I don't have your key.
No, it's not okay.
No, I don't have it. I should see it on my. No.
Ah, I see.
Oh. Yeah, because. Oh.
No.
Let me. Where is it?
I killed something.
Yeah.
I let it.
The
Where
one
is?
that
Oh,
is.
okay. And this is analysis. Is it very big one?
Ah, está bien.
Didn't work?
Yeah, the problem is the focus is a little bit bad for seeing the letters.
It's basically because if
I think
you
it's
check
okay.
on YouTube, basically we want to be able to see anything. That's the problem. So
So you want me to go back to the beginning of the talk or redo the talk? Or?
Yeah, maybe just the introduction.
basically, sorry about that.
No,
ya yo creo que ahí nos puede sentar. Ya,
So I keep my presentation, or and you
ya.
in another. Okay.
Todo sería normal, lo único que cambia es que nosotros colocamos la presentación ya en el programa para que desde que suceda.
Yeah, you continue the same, and they are going to put the presentation.
Okay, so I can use my.
Yeah, it's the same.
Yeah, which is better for me.
Pero nosotros también
Y vamos a así. Acá sí. Eso, mejor que le dan en un cuadrito ahí y la presentación ocupe todo.
No la cogió.
Desde precisamente muy esta people will be connected.
Stop.
Yeah, you can start again.
I can start again?
Sí.
Okay, so sorry for this interruption. I was talking about the different steps where the failure may find the root cause. So either in the design and selection of material and processes, manufacturing, control test, and of course use. So what we have to do is a preliminary survey. This is what we can do when we have a broken part in ends, and we have to gather general information. We have to look more thoroughly and precisely into the part, and then, if necessary, and only if necessary, we can do complementary exam. So the general information relates to drawing, design, material selection, fabrication routes, results of control, in-service monitoring, frequency of the failure, historical of the failure, identification of part, why not literature review. We can also make some reconstruction of parts, look to the aspects of the degradation, the fracture surface, and the related specimen fluids counterparts. With this, usually you can have a good idea of what happened, what occurred. But if you don't understand really and perfectly the failure, you can do complementary test or complementary exam, like metrology, chemical analysis, non-destructive testing, metallurgical analysis, microfactography, comparative tests, calculation, and simulation. And when you have done all this, usually you don't do so much investigation, of course, because you don't have anything to do that. But if you do all this, generally speaking, you will have the most likely scenario of the failure. The failure analysis is also a question of methodology. You have to be very thorough, and with a part you have to analyze. And this is very important, not to erase the aspects of degradation you have on the surface you are analyzing. Some data about the main cause of failure. This is some US statistics where you can find that 50% of the failure cause are due to errors in design. This is a lot. Not non-appropriate shape, erroneous selection of material. This is the main cause for a failure. The second one is the error in manufacturing, about 40%. And surprisingly, the least frequent cause of failure is due to the misuse of the part. These are also statistics about the cause of failure on 1,000 analyses performed by this French organism, setting. About more than one-third are due to fatigue, less than one-third are due to instantaneous fracture, 20% corrosion, 12% wear and abrasion, and a very low percentage due to in-service deformation without any failure. So why doing failure analysis? To better understand our system and component, to improve the component and system we design, and also to improve safety. When things fail, people can get up. And of course, to save money or to make money, make profits. So we have to wonder how long should a component last before it fails. Things break and stop working. Why? How long should a component last? This is our main question we have to wonder. We can design big components and systems to last forever, but they must last for their intended lifetime. And I want to define here the concept of bathtub curve. This is this curve, where you can see over time the failure rate. So the observed failure rate is this curve, bathtub curve. Usually when you manufacture parts, you have what we call the infant mortality failure, early failure of part due to mismanufacturing reason. This, of course, decreases over time. You have here the wear out failure due to the use of material and wear out failure. And you have here random costing failure. When you gather these three curves, you got this one. And this is very important to minimize this time to failure here, and also this one. Very important number. This is important to minimize the infant mortality failure. So this is a common way to analyze a mechanism of failure, and when you have to do a failure analysis, you have always to wonder on which part of the bathtub curve you are. Example of car tires. Infant mortality failure are covered by the warranty, very expensive for the manufacturer. Usually this is due to a defective product. Then this is followed by a long period where failures are very rare. And then, finally, you have to change your tires because they wear out. So, again, when you analyze a failed component, you have always to wonder where in the bathtub curve you are. It is also very important to do a failure analysis, failure statistics. To understand failure, we must track out failure over time, analyze each failure to find the root cause, and implement corrective action and project to eliminate most prevalent failure. When you aggregate failure statistic, even coarse statistic can give very interesting results. What broke? Where should I focus? What can I forget about? And divide your part into the product into meaningful section for tracking failures. This is very important as well. So accumulating root cause information over an extended period of time is very important for continuously improve product quality. This is very important to understand if these are infant or long-term failure, and this allows also to justify resources for corrective project or corrective action. Usually we use Pareto charts, giving that 20% of cause may be the reason for 80% of the failure, this Pareto analysis. So as a summary, I would say that analysis you must analyze as many failures as possible. You aggregate failure statistic over extended period of time, let's say 1 to 5 years. Understand your service life distribution, what percentage of infant failure you have, perform failure analysis, and create Pareto chart for failure cause or root cause. Launch projects for corrective action, and finally get profit in terms of financial issues. And you have also to report. So this is very important. Failure is always someone's fault and always carry a cost. So you need to defend your conclusion. People can get hurt during failure. These are legal consequences and financial consequences. So you have to be complete without any immaterial conclusion or evidence. You need a lot of work, of course, to do a failure analysis. So summarize it as bullet. Be concise and complete. And your report should allow also to understand the conclusion, work process, and reproduce the analysis if necessary. These are the main top misses in failure analysis report. Hurried or inaccurate stress analysis, never underestimate the importance of economics, and miss opportunity to summarize. So this is very important to go through this different point when you do a failure analysis report. Let's have a look now on the concept of failure chain. So what is failure chain? A sequence of events leading to a failure, and typically, if any one of these events had not occurred, the failure would not have occurred. So this is the example of the Lake Megantic runway train in 2013. Maybe you remember this catastrophe in Canada, where you can see here a photo. So let's have a look on the problem. This was a train parked in Canada on a runway trail. This was composed of 72 tank car, 5 locomotives, and for this train altogether, guess how many people was in charge? 1, 2, 3, 4, 5 more? The answer is 1. So this is kind of the first link in the chain. Only 1% for this huge train. Another link. To park the car during the night, we should have used a sliding track here and not a main line. But in this case, the sliding track equipped with a derail system was not available. So the train was maintained here in the main line. So this is kind of second link. Another link is due to a poor repair of an engine oil leak, which was repaired badly with only plastic adhesive. And the oil leak returned at the time of the catastrophe. So this is another link. If the engine had been repaired properly, probably no disaster. Okay. Another link of the chain. The train was parked, in 15 kilometers from Lake Megantic on a slope of about 0.7%. So to ensure the train not roll, it was necessary to leave one locomotive running all night, so that the brake system could operate, pneumatic brake system. The locomotive used for the locomotive with the oil leak. This is another link. If a different locomotive has been used, maybe no problem. Okay. So in the middle of the night, due to the oil leak, a fire caught fire near midnight. fighter extinguished the blaze after the first shutting down the locomotive. But they did not restart the engine or the engine of another locomotive. So no more pneumatic brake available. Okay. And here we come back to the only one person in charge of the project of the program of the train. The person has to make manually to put in operation manually the brake of all the wagon here. So another link here because no time to do that, very long time to do that. And this is about, something like 1 minute per car. Yeah, 1 minute per car. So you can see 72 cars plus 5 locomotives. Very long time. Okay, very long time to put the handbrake wheel in operation. So this is another link. And you can see for the slope, if you do very simple calculation, we should have provide this force for this slope here, this force to make the train stop. And the estimated force applied by the handbrakes put in operation by the only one person in charge of the train is about 1/3 of the necessary force to make the train stop, to have the train not rolling. So, very low force, very difficult. Okay. And another link is that the tank car used were not designed for hazardous or flammable product. So this is also a mis-choice in the quality of the car, of the tank car in the train. So this was a disaster. Some photo here. So you can see an illustration here of what we call the failure chain. Different steps or different problems that occurred at the same time or consequently to each other. So this was the disaster. Okay, so now going back to mechanics of material here, I would like to show you that the first thing is to perform what we call morphological analysis, where you look to the fracture surface of the material. And the orientation of the fracture failure, of the fracture surface, is related to the type of stress and the nature of material. A very simple example here, in tension, when you load a ductile material, because the ductile material is sensitive to shear stress, you will have 45-degree surface failure with respect to the loading axis. Whereas for a brittle material, you will have a failure surface 90 degrees perpendicular to the loading axis. Because brittle materials are more sensitive to normal stress than they are to shear stress. If you do the same for torsion loading, the ductile material will show the fracture surface more or less perpendicular to the loading axis, whereas the brittle material will have a 45-degree surface failure to the loading axis. And this is due to the nature of material and the nature of stress tensor in the material. So this is sometimes very easy by just analyzing the orientation of the fracture surface with respect to the loading axis to determine whether you have a brittle or a ductile material. Or if you know very well that you have a brittle or a ductile material, you can consider critically the type of loading and have some information on the type of loading. So very interesting to just look with your eyes. No need of sophisticated equipment, of sophisticated microscope to do that. Only your eyes can give very valuable information. So the fracture in material can be either transgranular, when the fracture surface crosses the grain of the material, or intergranular, when the fracture surface bypasses the grain. So the intergranular failure are given here: brittle rupture by decohesion, creep rupture, corrosion rupture. And the transgranular fracture are ductile rupture, brittle rupture by cleavage, or fatigue rupture. You can also consider the fracture surface of material by their observation or their kinetics here. Fracture can be either instantaneous or progressive. Instantaneous in the case of ductile or brittle by cleavage or by decohesion fracture, and progressive in the case of fatigue, creep, and corrosion as well. So this is interesting to check here, either by the observation or by the kinetics of rupture, what type of rupture you want. These are the main characteristics of the ductile rupture. You have always or often plastic deformation close to the surface, and on the macroscopic aspect here you can find matte surface, plastic deformation, necking if the tensile, if the applied load is tensile, no visible zone of initiation and propagation, and often high roughness surface. And when you go to the microscopic scale, you can see large dimple here, a large number of dimple, orientation, and inclusion. These are phases, brittle phases, non-deformable phases, around which the deformation, the plastic deformation can occur. The brittle rupture by cleavage are given here, where the fracture surface cross the metallurgical grain of the material. So you have no plastic deformation here. This is a brittle fracture. Plain and bright surface, no visible zone of initiation, propagation, no plastic deformation. And when you go to the microscopic scale, you can see lots of cleavage planes. These are given here in the micrograph, and visible direction of cleavage here, you can see. By decohesion, no plastic deformation again, because this is brittle. You have a plain surface, no initiation zone, no propagation, and you can see at the microscopic level juxtaposed polyhedron here, possibility of secondary crack, as you can see here, for example, or here, and brittle phases at grain boundary, possibly. Creep fracture, so you have surfaces with dull facets, no visible deformation, at least, no initiation traces, no propagation. You can see here an example of this kind of fracture. And when you go to the microscopic scale, you can see that the fracture is intergranular, you can see pores, and you can see also vermiculates in oxidizing atmosphere as well. Corrosion fracture, highly variable here. You can see traces of oxidation, of corrosive products, of corrosion products, and here also in some cases, for example, in the cases of aluminum alloys, you can see some exfoliation as well. The microscopic aspect reveals that the fracture is intergranular, and you can see possible secondary cracking as well, and possible ramification due to the corrosion, intergranular corrosion in planes, making an angle with a main surface fracture. This is the first example I wanted to show you. This is a case study we do with our student, which is the case of a nitric acid reservoir with two deep drawn bottom and a central ferrule here. And you can see here the damage of the bottom of the reservoir. You can see here the welding between the ferrule and the bottom. And you can see here the material, which is stainless steel, very typical microstructure of the stainless steel. This is an optical micrograph of the Philippe, and here you have the damaged part, which is somewhere here. So you can see very simply here that the failure is due to some corrosion, and when you make a higher magnification image here of the part that is damaged, you can see that the corrosion is intergranular, which is often the case, and you can see in the metallurgical grain of the material some slip traces. And these slip traces are probably due to some deformation in the material. And this is the part here which is deep draw. And usually speaking, when you deep draw a part, you do that at low temperature, at room temperature. So usually you have to make heat treatment afterwards to release the stress. And you can see here a very interesting image showing the heat affected zone of the bottom side. So this is somewhere here. And you can see here a very, very small metallurgical grain, indicating that the material has recrystallized, in this part. So, you know that the welding here brought some high temperature in the vicinity of the welding here, and because you have some deformation due to the deep drawing of the bottom, you can have recrystallization. You need temperature and critical deformation to be able to recrystallize. So this is another evidence of some residual stress in the material here, in addition to the analysis of this image here. So probably here we have a case of what we call stress corrosion, combination of corrosion by nitric acid and some stress, some residual stress in the material. So the corrective action here would be either to do the deep drawing process at high temperature so that you can have some recrystallization, what we call dynamic recrystallization, or doing the deep drawing at room temperature, which is the usual process, and then make a heat treatment afterwards to get what we call the static recrystallization, doing the recrystallization of the grain after the deep draw. And in this case, no more stress, residual stress in the deep drawn part, and no stress corrosion, probably. So this is a very simple corrective action here. Cases of fatigue here is very interesting to analyze fracture in fatigue, because usually speaking, the fracture surface is very typical. You can see three zones, very simply you can see two zones. Here, the first zone, where you can see that the surface is smooth and silky, and the second zone here, where the surface is very rough, okay? So, when you have considered these two zones, generally speaking, by analyzing the zone of crack propagation here, this one, you can find the third zone, which is here, the first one, where you get the initiation of the crack. Okay? So, on this part, which is the zone where the crack propagates after its initiation on the defect, you can see beach marks, frontal marks, and ridge marks, which are radial marks. Okay? And see, if you go here to the final fracture, you have a fracture which is ductile and you have a rough surface. From the microscopic point of view, if you analyze first this one, the zone where the crack propagates, you can get fatigue striation. These are illustrated here. This is illustrated here, when you can see each striation here corresponding to each fatigue cycle on the material. So this is very interesting to analyze what we call the interstriation distance. This gives some valuable information on the level of stress and the resistance of the material. And if you go to the first zone, probably with this microscopic approach, you can get some information about the initiation, either some metallurgical defect like inclusion or surface defect due to, for example, machining of the material. So, very interesting to analyze fracture surface in fatigue. I give you here an example where you consider the fatigue of material or fracture mechanics of material. You can see here the failure analysis of beverage can. So you can see here that this can has failed, and when we analyze the problem here, we can see that we have some corrosion in the inside part of the can. The corroded area was long and slender, and the corrosion was probably a result of a defective internal coating. Let's have a look on this economic aspect. You know that is one rupture in 1 million cans can be okay for the industry of aluminum can. In the US, about 100 billion cans per year. So one rupture in 1 million make 100,000 fracture per year. And for the aluminum industry, at least in the USA, aluminum beverage cans is more important than airplanes or cars. About this number of cans, about this weight for each can, this is about 1.5 10 to the 9 kilogram of aluminum per year to manufacture this. So, fracture of can be very bad for business, and this can industry, of course, want to understand cause of failure, the condition, cause failure, and effect of loss of variable methodology. So, one of these is the thickness of the can. Of course, the alloy can be also considered, the grade of alloy, the processing, and the coating. But let's have a look on the thickness here. So, usually here the thickness, the nominal thickness is about 100 micrometer. If you look to the manufacturing cost for doing the can, it's about $0.05, and the beverage inside is about $0.01. So about 80% of the cost is due to the material and not to the beverage that you put inside. So this is very important. If you reduce the thickness from 100 micrometer to 99 micrometer, you can save tens of millions of dollars. So this is very important to have a look on this parameter for saving money. But if you reduce the thickness, maybe you can make fracture more likely. So we are here in the case of the fracture mechanics approach, and no more in the material strain approach, where you compare the applied stress to the yield strain of the material. Simply. In the case of fracture mechanics, you have to consider the applied stress and to compare it to the crack size, the size of the possible crack of the material, and the toughness of the material. This is a little bit more complex. Okay, so we will do, and I will show here an analysis on the leak before break theory. Okay, it's always better to have a leak than a break or an explosion. And what controls leak versus break? So we have this aluminum can example here. You can see here a leak, not so much a problem, and you can see here an explosion, much much more severe problem here. So, as I said before, a leak is always better than a break. So, what controls this leak versus break? The dimension of the pressure vessel, of course, the type of material, the fluid under pressure, the pressure level, and the size of flow or damage. So we will focus on this and this. Okay, let's have a look on this parameter here. Let's say we have a flow or a defect at the surface, external surface of the can, this length and this depth here, L and A. Okay, so the thickness is 100 micrometer, as I said before. So what we do here, we increase the pressure in the can, in the reservoir, and try to find when crack props through. So here we have to consider what we call the stress intensity factor. When you apply the stress on a material containing a defect with this size here A, you will get a stress intensity factor, which is expressed here as the applied stress times geometrical constant and the square root of the size of the flow. If the stress intensity factor is lower than the toughness of the material, in this case you have a leak. If the stress intensity factor is greater than the toughness of the material, in this case you have a break. Okay. So with this test here, where for a given scratch length, here 6 millimeter, we increase the pressure and look whether we have a leak or whether we have a rupture. And you can see that at this level of pressure, we have only leak. If you increase a little bit the pressure, you can get leak, and then leak, and again leak here, and then the fracture of the material. Then we did this test for different scratch length, increasing from 6 millimeter to 12 and 18, and again we repeated this same test by increasing the internal pressure. And you can see that we could discriminate two domains where you have leak below and a rupture above this, this line here, which is given here. Here you have the stress intensity factor lower than the toughness of the material, and here you have the stress intensity factor higher than the toughness of the material. Of course, what we can do, or we want to do, is to move this curve here on the right and on this part here. We have to move this. So, what can we do to move this curve up and right? Cyclical. We discussed before the problem of increasing or decreasing the thickness of the can. Make the can with material with higher toughness, more tougher alloy. Put some coating or solution. So this is a very interesting study, very simple study to address the problem of material or design of the part to avoid or limit as much as possible the fracture of the can. Starting from this, you can, for a given pressure here, define a critical length of defect. You can see here, for this pressure, which is pressure in the can, you have a critical length of the crack defect, about maybe 7 millimeter here. Below this, no problems. Above this, you can have problems. Okay, other example here, which are more connected with the aerospace industry, which is the domain in which I work preferentially. So here you have a turbine, a wheel of an helicopter engine. This is made with a nickel-based superalloy, and we suffer this fracture here of a blade, you can see here, after 10 minutes of service, very low time of service, and after the rotation speed reached 32,000 rotation per minute. This is the helicopter engine produced by a French company, which is a Safran helicopter engine. So you can see here a very rapid failure, which means that probably there was not enough time for fatigue of the material. And you can see here, close to the fracture, you can see here some plastic deformation. And you can see here on the fracture surface itself that you don't discriminate two zones. So probably no fatigue here, only an instantaneous fracture of the material occurring very, very quickly. So this is what we call a ductile fracture, because you can find here some plastic deformation, and an instantaneous fracture, not relating to any fatigue of the material. If you go more deeply in the analysis, you can see here quite nice microphotography of the material, and you can see on this micrograph very typical gamma prime microstructure, two-phase microstructure, very typical of nickel-based superalloy. So the material, in terms of its microstructure or phase structure, is okay. But if you go more deeply in the analysis, you can find here what we call micro piping. You can get in the microstructure of the material a lot of pores. You can see here. And this is an analysis to evidence the presence of pore here. You can see here the scale. You can add in the material a lot of defects due to the manufacturing. When the material, the part, was produced using casting processing, the casting was not perfectly performed, and you got some casting defect in the material, okay? leading to this the presence of preferential crack at the tip of this metallurgical defect. So, and this occurs very quickly because you get a lot of foundry of casting defect in the material. So this is a case of ductile instantaneous fracture due to metallurgical defect resulting from a bad manufacturing, bad casting material. Another example here, where you get here the material, the nickel chromium molybdenum steel, this grade, which is okay in terms of standard compliance, and on which we did harness measurement. On flanks, we got about 700 to 720 Vickers, which is okay. And in bulk, we get 430, which is also okay in terms of standard compliance. The material is harder at the surface than in the bulk because you have here turbine gear, and you must be very hard at the surface because due to the mode of loading contact between the two parts. You can see here very typical fracture surface where you can see the two zones I detailed before. The zone where you have the propagation of the crack, and here the final fracture occurring on the very last cycle. And here you can see the beach mark I detailed before. And when you consider the concavity of the beach mark, you can go very easily to the initiation point, which is here the point where the zone where probably the stress intensity factor was the highest. So the initiation of the crack was somewhere here, and then the crack propagated this way until the material was not until the surface, the remaining surface of material was not enough, sorry, to support the loading. Okay? So this is typical of fatigue fracture here. And when you analyze perfectly here, or more at a higher magnification, you can see that you get a lot of crack, and that these crack are precisely the, the size of the zone at the surface of the material, which were hardened using diffusion of carbon. To get a hard surface in that part, we used to enrich the surface of the steel with carbon, because it's cementation, okay, back cementation. And you can see here that the cementation was not properly conducted. As you can see, the carbide here, iron carbide produced by the enrichment of the surface with carbon, are poorly disconnected to each other. So, in other words, the carbide particles are connected to each other, which make a preferential path for the fracture to propagate. Okay, so this was the reason of this failure, the poor surface treatment produced on this material. Okay, and I show you the last example here, which is the fracture of turbine blades on the first stage of an helicopter turbo engine, again, and the damage occurred after 972 cycles, about 547 hours. The analysis of the material showed that the grade is this Inconel 100, which is okay with us in terms of standard components. So you can see here the fracture of the first stage blades, and you can see also that after fracturing those blades, damage the second stage as well as the third stage. So all stages are damaged, but the root cause was inducting the first stage blades fracture. Again, here a very nice micrograph showing the typical gamma prime microstructure of the nickel-based superalloy. No problem with the material here. And here you can see again the two-domain fracture surface, very typical of a fatigue fracture surface, with an initiation here and a propagation through this zone, and then the final fracture here. You can see about the same thing here and about the same thing here. So fatigue again here. And when we did the analysis of this, so we have a higher magnification image here of the fracture zone, where you can see mostly here the zone where the crack propagates prior to the final fracture, which is here. And when we do the measurement here, this zone of fracture, of crack propagation, is about this length, and considering the number of cycles, which was about 1,000, 972, we can determine using the measurement of the fatigue zone here what we call the interstriation distance, so characteristic of each cycle. And we found something like this 3.5 micrometer. And here you can see a micro photograph of the zone, a very high magnification of some part here in the fatigue zone, and you can see the fatigue striation, characteristic of the fatigue propagation, the crack propagation during fatigue. And if you go back to the measurement, and if you consider the interstriation length calculated here with this quasi-microscopic view of the material, the damaged material, we should have only 6 striations over this length here, about 22 micrometer. And obviously, we have much more than 6 striations here, maybe 1, 2, 3, 4, 5, 6, 7, and if you continue, maybe 20 or 25 striations here. So the conclusion here for this case study was to say that probably there was an additional fatigue loading in addition to the nominal loading, which was considered as vibration. So you have the nominal loading in fatigue to some vibration because the blade was not mounted on the disc properly. So vibration plus fatigue loading makes that the fracture of the part of the material occur more earlier than expected. Okay, so I just finish with this 3 case studies. Thank you very much for your attention. Thank you. Merci. Gracias. It's very strange to talk with nobody or only 3 persons.
Reminds me that the days of the opera.